Now coming to the type of hybridization. So in the last AV I have told you about sp3 type of hybridization. I have also discussed a little bit about difference between sp3 and sp2 in terms of pi bond, that how a pi bond is weak, that I have discussed with you. Now today I am going to discuss with you that is the sp2 type of hybridization, sp2. So sp2 type of hybridization basically is being shown by those molecules which are trigonal planar in nature. So which molecules are trigonal planar in nature? Basically alkenes, we can say that. They are trigonal planar in nature. That is, it has got carbon-carbon double bond in which the sigma bond undergoes hybridization, but again I repeat, the pi bond does not undergo hybridization. So as pi bond does not undergo hybridization, you will find both the lobes are of same size, of equal size. But the one which undergoes hybridization, you will find one of the lobe is bigger in size, another lobe will be small in size. Got it? Clear? And it is trigonal planar in nature. So otherwise I can say the molecule which is trigonal planar shows sp2 type of hybridization. Alright, the bond angle is 120 degrees, so to say. Clear? So it has got carbon-carbon double bond. So alkenes means propene, ethene, butene and all these things. These molecules undergoes what you can say sp2 type of hybridization, so to say. Got it? Again I repeat, carbon-carbon double bond. Or any other molecule showing trigonal planar shape also shows what you can say this sp2 type of hybridization. Like suppose boron trichloride. Got it? Boron trichloride, BCl3. It is nothing but B and 3 chlorine which is attached to trigonal planar structure. That is 3 chlorine. It is attached in this particular manner. Boron trichloride. See here. So bond angle is how much it is? See here. I can draw it in this way. The bond angle is here. It is 120 degree. So it is again trigonal planar in nature. So BCl3, BF3 in this way. Any molecule which is trigonal planar also shows sp2 type of hybridization. So idea or I have said you already, by this we can come to know, from the shape we can come to know, or from the hybridization we can come to know the shape, whatever it is. Now let us see the formation of ethene molecule here, the floral diagram for the formation of ethene molecule. The same thing, you need to write the electronic configuration. The initial process is the same, only the diagram is a different. We can say that. The initial process is the same. We can say that. So what you will do is that ethene is nothing but CH2 double bond CH2. So one carbon has got 2 hydrogen. Similarly another carbon has also got 2 hydrogen, isn't it? Clear? So what we'll do is that carbon, it is 6, 1s2, 2s1, 2px1, 2py1 and 2pz1. Alright? Similarly hydrogen, it is nothing but 1s1. So here it is 2s1, 1 you can get it here, and in case of p subshell you can see 1 unpaired electron is there. So the first I said 2s and 2s, see carbon-carbon bond will be formed. So one subshell of carbon atom having 2s subshell and another carbon atom having 2s subshell, first they undergo head-on overlapping. Alright? 2s subshell of one carbon atom and the 2s subshell of another carbon atom, because another carbon atom also will have the same configuration. So they will undergo first of all head-on overlapping first. So I have already said you that 2s subshell will undergo head-on overlapping, always carbon-carbon bond formation. Always first, that is one, this particular subshell will undergo carbon-carbon bond formation, because first the skeleton has to be formed. Then only you will be adding the other atoms into it, isn't it? So here what you will find is that, here what you can find, that is 2s of another carbon atom will come, here 2s of another carbon atom, and here the 2px and 2py will participate in bond formation, that is 1s1 and 1s1, we can say that. So here what you find is that 1s subshell of the carbon atom and 2p subshell, p plus p, px and py subshell of the another carbon atom participate in bond formation. That means I should say that is here the S subshell of the carbon atom, because always remember carbon atom is undergoing hybridization, not the hydrogen. I told you earlier also. So this is your 2s subshell and 2px subshell. You can show in this way. The 2px subshell, got it, undergoes hybridization, as well as that is nothing but 2py subshell undergoes hybridization. This, if you take it this as y, so this is your 2py subshell undergoes hybridization, we can say that 2py. 2pz subshell does not undergo hybridization, 2pz subshell. So it remains as it is, we can say that 2pz subshell does not undergo hybridization. Clear? You can see it here. Because what I said, CH2. So here one hydrogen and here one hydrogen will come, isn't it? Here if another hydrogen is coming, it will become CH3. This is carbon. So here carbon-carbon bond will be there. And the remaining will be with hydrogen. So how many? One carbon contains how many hydrogen? 2 hydrogen. So here one hydrogen and here one hydrogen. Finished. CH2. Alright, so which subshell is participating? 2s subshell, 2px and 2py subshell is participating. 2pz does not participate in hybridization in bond formation. Alright, so it will undergo which bond? Pi bond. We can say that. Now we will see the floral diagram. If you want, you can mix it up this one and you can show it in this manner. That is 2s and 2px, 2s, 2px and 2py. Alright, similarly 2s of another carbon atom, this is 2px and 2py. So they undergo bond formation. Got it? Hybridization. So how many subshell is involved? 1s and 2p subshell. So hence it is nothing but sp2, I should say. Or I can write it here also sp2. We can say that. So as 1s subshell and 2p subshell is involved, px and py. So it is sp2. We can say that. Very simple. Theoretically also we can find it out. I have told you by the help of formula also we can find it out. In this way we can say that. Clear? So now we need to show the floral diagram. So how the floral diagram will be there, that is see it. That is important, the floral diagram. So for the floral diagram, see here, carbon atom, first of all 2s will overlap. I have said you S subshell will be this, even if a subshell is spherical, but it is not an atomic orbital, it is a hybrid orbital. I have said you already. Now it is trigonal planar, so you have to draw trigonal planar only. See here, see it is trigonal planar. See now, trigonal, same thing. It should also look like trigonal planar. Understood? It should look like Jabardasti nahi. So in this way, sp2 sigma, this is one hydrogen, this is hydrogen, we can say that. Clear? Same thing here, also same thing, sp2, this is sigma bond, this is hydrogen atom, this is sp2 sigma and this is hydrogen atom. Clear? Understood? Now px and py, here also px and py undergoes, and 2s undergoes bond formation. Now what about pz? See here, pz remains as it is. Pz, this is your pz subshell, it remains as it is. Now the opposite lobe of px will be a smaller one and the opposite lobe of py will be a smaller one. Here also same thing, the opposite lobe of px will be smaller. You can take any one as px and py, understood, and the opposite py will be a smaller one. We got it? Done. Now finished. So this undergoes, what is that? Pi bond. So this is pi bond. Now pi bond is delocalized. It can be either above the sigma bond or below the sigma bond. I have already discussed with you. Don't think here 2 pi is there. No, only 1 pi. Either it can be above the sigma bond or it can be below the sigma bond because it is delocalized. Alright, so this is your, what you can say, the trigonal planar molecule of ethene molecule. Now I need to draw the equivalent diagram. See, the equivalent diagram will be in this way. The equivalent diagram. This is hydrogen, 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 sigma, sigma. This is also sigma, sigma, sigma. The bond angle is 120 degree. You will write it here trigonal planar. I don't have the space. Alright, and you will draw an electron cloud either above and below. This is nothing but is your pi electron cloud, you should say. Alright, clear. So this is the equivalent diagram of ethene molecule, so to say. We can say that. Clear? Understood? Done. So this is sp2 hybridization. Now here the bond length will be, already I have said you, it will be nothing but 1.34 carbon-carbon bond length will be 1.34 angstrom. Alright, carbon-carbon bond length. Clear? And if you don't understand, you can make a single bond also. If you don't, actually I have done a pi electron cloud, I have done it. If you don't understand, you put a single bond and you write here a pi. It will do, no problem. Alright, so it is 1.34 angstrom and here it is nothing but 1.08 or 1.09 angstrom, so to say. Carbon hydrogen is 1.08 or 1.09. Okay? So in this way you got it for the ethene molecule, the floral diagram. Now we will come to the ethyne molecule. Ethyne. So ethyne means C2H2. We can say that. So here C2H2 molecule will take, the shape is what? Linear. Ethyne is, the shape is linear. We can say that. Clear? Carbon-carbon bond length, you may write it down. It is nothing but 1.2 angstrom because it will become still smaller. I have told you in the last area. As the number of S subshell, because in case of sp hybridization, S is 50%. So bond length is going to decrease. As there is an increase in the percentage of S character in hybridization, bond length decreases. Why? Because the atoms come closer to each other. So hence the bond length decreases. So in case of sp3, single bond, carbon-carbon single bond, you are having 1.54. Alright? In case of carbon-carbon or any other molecule, I am not saying that. In case of carbon-carbon double bond, it is nothing but 1.34 angstrom. And in case of carbon-carbon triple bond, which I am going to draw it now, you will see it is 1.2 angstrom. And carbon-hydrogen is same thing, is 1.08 or 1.09 angstrom, so to say. The bond angle is 180 degree. It is linear. Bond angle is 180 degree. And the bond dissociation energy is very, very high, which is 811 kilojoules per mole. 811 kilojoules. In case of carbon-carbon double bond, you have seen it is at 614 kilojoules per mole. And in case of carbon-carbon single bond, it is 384 kilojoules per mole. So you can imagine from here, you can get an idea from here that carbon-carbon triple bond is such a strong bond, so large amount of energy is required to break the bond. So hence the bond length has to be smaller, we can say that, isn't it? So here I am not drawing the initial part, you can understand it, that is we have to write the electronic configuration of carbon, and for hydrogen same thing, 1s2, 2s1, 2px1, 2py1, 2pz1. Then which subshell is participating in hybridization? Only 2s subshell and 2px subshell, because what I said, it is nothing but HC triple bond CH. So which subshell is participating? 2s subshell is participating in hybridization and 2px subshell is participating in hybridization. 2px is participating in hybridization, so to say. 2py and 2pz does not participate in hybridization, only because one will be carbon-carbon, so 2s subshell will participate, 2s subshell of one carbon atom and 2s subshell of another carbon atom. Already I hope you understood from sp3 and sp2. They will participate first. First that will be taking place, skeletal will form, I have told you already. Then after that 2px will come. In 2px, one hydrogen atom will participate in bond formation. One hydrogen atom, because one hydrogen is there, with one carbon, one hydrogen. With another carbon, another hydrogen, same thing. So whatever the hybridization is with this, the same thing with this also, it will be same. So in this way, what we find is that is 2px is participating, 2py and 2pz remains unhybridized. We can say that. It remains unhybridized. So this part is, it is being clear to you. It is, you will be doing it in the same way as you have done it in sp3 and sp2. Now coming to the floral diagram. That's the most important part. The floral diagram. So in the floral diagram, what you see is that is 2s subshell and the 2s subshell of another. Got it? So first, so it is sp. So sigma bond. Now here it is and here it is. This is what? 2px. This one is 2s of carbon atom. They participate and they form bond formation. Sigma bond. Now this is your 2px of one carbon atom and 2px of another carbon atom undergoes bond formation with hydrogen. We can say that. So what is that? Sigma bond. So it is sp. It is sigma bond. Hydrogen. Alright, so you can see it is linear. It is linear. And the opposite lobe of 2px will be here. It is smaller. And the opposite lobe of 2px is smaller. See here, the opposite lobe. Alright, try to understand very clearly. This is 2px. One lobe will be bigger and the lobe will be smaller. See, I have done it inside only. Here also this is 2px. One lobe will be bigger and the lobe will be smaller. I have done it inside. And this is your 2s and 2s. Already I have said it. Alright, say it is linear. Bond angle is 180 degree. Can you see? It is linear. Now 2py and 2pz will be unhybridized. So both the lobe will be of same size. So this is, let us say, 2py and this is, let us say, 2pz. Alright. Again this is 2py. Alright. Listen carefully and repeatedly. Once if you don't understand from the AV, twice, thrice you see it. Alright. That is the main purpose of sending the AV is this. Because you can see it repeatedly and you can understand it. Because very clearly I am saying you. So this is your px is gone. Px bigger and smaller. Another px of carbon atom, this is a bigger low, opposite low will be smaller. Hydrogen, hydrogen gone. Fine. This is py, py. Pz, pz, both the lobes you can see of same size. Same thing py, pz, pz, both the lobes are same size. So this is py and py, this is pi bond. Again py, py, it is pi bond. Got it? So you got pi bond. Same thing, pi bond can be either above or below. So this is another pi bond. Got it? And this is another pi bond here also. Either it can be above or it can be below. You can see in this way. Clear? Now the equivalent diagram is this. This is the equivalent diagram. We can say bond angle is 180 degree. This is 1 sigma. This is sigma. This is sigma. This is pi. This is pi. We can say that. Clear? One sigma bond and both pi bond we are having, and it's a linear molecule, we can say that. Okay. So this is about your sp hybridization. So any molecule which is linear in nature. So linear in nature, which molecule it will be? This is organic. Inorganic molecule, just like in sp2 I said, it will be your BCl3, boron trichloride. Similarly, it can be BeCl2, beryllium chloride. Alright, beryllium chloride. See, this is linear. Beryllium chloride, we can say beryllium fluoride. In this, so many molecules we can have it. It's not just one, like carbon dioxide, CO2. Alright, it is linear. CO2, it is linear molecule. Already I have studied in dipole moment. I have studied it is linear in nature. It has got sp hybridization. Alright, but you will say that's a double bond sp, double bond. It is not carbon carbon double bond. It is carbon oxygen double bond. It's not carbon carbon double bond. Double bond means not with any atom. I said carbon carbon double bond will be sp2. Here carbon oxygen on either side and carbon oxygen on this particular side. So it is for that reason the dipole moment you can see it is being cancelled, and hence the bond angle is 180 degree. You know it is linear in nature. Alright, clear? Understood? Fine. So this is about your sp3, sp2 and sp hybridization I have told you. Next, in the next area.